Next up, we have Chip Shearer, and he's going to talk about the Apollo Next Generation Sample Analysis Initiative. This is something that we've been kind of referencing in the talks prior to this, but now Chip's going to give us some in-depth information on it. So Chip, are you there?
Yes, I am. Can you hear me?
We can. It's all yours.
Okay, wonderful. Thanks. Wonderful. Well, the Apollo program returned. Could I have the next slide, please? Yes, the Apollo program returned approximately 382 kilograms of a variety of lunar rocks and lithologies that were collected and stored in numerous ways. Both Judy and Jack summarized some of these tools and approaches. And some of these samples that were collected remain sealed. They're fairly unique, or samples were uniquely curated. These special samples are the target of ANGSA. Can I have the next slide, please? In some of these lithologies, there are mineralogical, chemical, and textural evidence that may reflect the role of volatiles in lunar processes. Several are showed here just as examples. For example, coatings on barnacle glasses that have been documented with a volatile element stratigraphy in some cases. Glass surfaces that have been oxidized have been documented. And again, some work that I've done on sample 66095, the rusty rock, suggests within that rock there may be some hydration and oxidation of those rocks. The problem is, are these lunar processes or reflective lunar processes or some sort of terrestrial modification? Next slide, please. In that exploring volatile reservoirs, the sources of volatiles, and the utilization of volatiles will be an important component of Artemis. Sampling volatile-bearing materials and storing them must be well understood. One step is to examine the special Apollo samples that is being carried out by ANGSA. Next slide, please. Very early on, Apollo scientists and engineers recognized these potential problems of terrestrial contamination, either on Earth or in the crew cabin, and designed a variety of different types of containers to protect selected number of samples. This chart just illustrates two, again, that Judy discussed. The gas analysis sample container, which had a volume of 70 cubic centimeters, special environmental sample containers, which were a bit larger. In the next slide, just illustrates the larger of these sealed vacuum containers, and those are the core sample vacuum container, and you can see the relative size of the CSVC compared to the special environmental sample container. There are only two of these containers used during Apollo 6. There are only two of these used, one during Apollo 16 and one during Apollo 17, and neither have been opened. When they were returned, they were placed within vacuum containers, and they've been stored in a pristine vault for more than 45 years. These containers, all of these types of containers, work on this principle of an indium seal, a knife edge on the upper portion of the container, and the indium seal top is pressed into the knife edge and locked in, sealing that container. Next chart, please. The ANGSA initiative is looking at three different types of samples. One is these unopened vacuum sealed Apollo samples, and our focus is on 73001 and its companion double drive tube 73002. Frozen samples that were frozen and remained at minus 20 degrees centigrade since their return. They weren't frozen on the surface, however, and Apollo samples that were uniquely processed, curated, and stored in helium. Next slide, please. The Angsta Consortium consists of 9 original teams and over 60 scientists and engineers. The ANGSA is designed as a new lunar sample return mission, which involves processing, preliminary examination, and analyses utilizing new and improved technologies and incorporating this into recent mission observations. And finally, ANGSA is a multi-generation science team that kind of links the first generation of lunar explorers with future explorers. Next slide. The double drive tube that consists of 73001 and 73002. The lower portion of the drive tube, 73001, was put in this unique container. It was collected in the Taurus Littoral Valley at Station 3 during the Apollo 17 mission, and it penetrates this light mantle deposit, which again appears to be a landslide deposit. This is both a continuation of Apollo goals and Apollo science, but also feeds forward to Artemis. Next chart, please. This just illustrates a comparison of older technologies with brand new technologies. The first two diagrams here that are listed 1974 are X-ray analyses of the core done in 1974. This is 73002, and a accompanying map that was made from this X-ray map. As you can see in the lower part of that diagram, that is the X-ray computed tomography image, which increases the resolution incredibly, and provides a strategy for dissecting and carrying out science. But also what one can do with this is essentially look at different slices through this, perhaps thousands of different slices, and look at the petrology and mineralogy and texture of these rocks. Next slide. In the last core sample that was processed at JSC was in the 1980s. So there was a large learning curve for our new generation of lunar processors to come up on. And they were extremely successful in extruding the sample. In addition, the ANGSA PE team was involved in examining and the dissection of the sample using digital imaging, electronic record keeping, multispectral imaging, and hyperspectral processing. So we are in these processing, not only are we learning, but we're moving forward in applying these new technologies. Next on the agenda is core processing of samples. Next slide. This just illustrates one of our strategy diagrams that just illustrates the flow of materials from initial collecting preliminary examination data through actually sample analysis science. The PE measurements are shown in green, the sample analyses are shown in pink, and this is only done with a little over 200 milligrams of material. Next slide. We are also focusing on how do we open the core sample vacuum container and extract or investigate if there is any gas that came from the sample. Although smaller gas sample containers were opened during Apollo, a strategy and tools for opening the core sample vacuum container were never finalized. During ANGSA, we have a core sample vacuum container strategy and have developed piercing tools and a gas manifold to select, to collect, and analyze this material. The final slide illustrates—
About 30 seconds left.
Yeah, the next slide is the final slide and just illustrates some of the links between ANGSA and Artemis. ANGSA is a multi-generational initiative being run as a sample return mission and therefore trains future generations. We're investigating what worked and what didn't work during Apollo. And then finally, we have the availability of a variety of new curation and analysis tools that we can use on these samples that, again, feeds forward to Artemis. Thanks.
All right, thank you, Chip. That was super helpful, and I think a lot of folks were curious about ANGSA since we've been kind of referencing it throughout the morning. So now we have a good sense of what actually is going on for ANGSA. So that's
Great.
awesome.